Hi everyone, my name is Shuai. I'm a PhD student at UW Medicine. Today I'm going to present our paper, Contraction, a unified perspective of course decay and zero-freeness of two-spin systems. It's a joint work with Yuxin, who is also a PhD student at UW Medicine. So let's introduce two-spin systems. Two-spin systems are models from statistical physics. It models interactions between neighbors on graphs. A two-spin system is specified by two edge interaction parameters, beta and gamma, and a uniform external field, lambda. And an instance of a two-spin system is a graph, and a configuration is a mapping that maps each vertex to a spin plus or minus. For each configuration, we define weight. It's a product as follows, and here we consider the number of plus edges and the number of minus edges, and also the number of vertices that are pinned to spin plus in this configuration. And the partition function of a two-spin system is the sum of weights over all configurations. So it's a sum of product computation. And when a two-spin system is restricted to graphs of degree bounded by some delta, we see that such a two-spin system is delta bounded. While in classical physics, these parameters are usually non-negative real numbers, and we assume that they are not all zeros. And such two-spin systems are divided into two cases, the ferromagnetic case and the antiferromagnetic case. And when these parameters are non-negative, the partition function is also non-negative, actually it's non-zero and it's positive. And then it's the normalizing factor of the Gibbs distribution. It's a distribution where of configuration is drawn with probability proportional to its weight. And however, it's meaningful to consider complex parameters. By analyzing the location of complex zeros of the partition function, phase transition was discovered in statistical physics. Well, one of the first known and also the best known result is the Leon circle theorem. And in this talk, we will the partition function as a multivariate polynomial over these three complex variables, and we study zeros of this polynomial and its relation to the approximation of the partition function. Now, the partition functions encode rich information about two-spin systems. They are not only of significance in statistical physics, but they are also well studied in computer science. So the computation of the partition function of two-spin systems is the most basic case of counting graph homomorphisms and counting constraint satisfaction problems. These are the two well-studied frameworks for counting problems. And there are many natural problems that can be formulated as two-spin systems. For example, when beta equals gamma, this is the famous Yuxin model. And when beta equals 0 and gamma equals 1, then the partition function is an independent polynomial of a graph. It's also known as the hardcore model in statistical physics. Well, for exact computation of the partition function, the problem is proved to be sharply hard for all complex valued parameters, except a few very restricted settings. So the focus is to approximate the partition function. And the goal is to devise a fully polynomial time randomized or deterministic approximation scheme. They are called FPRAS or FPTAs. It approximates the partition function with a factor of 1 plus minus epsilon, and it runs in polynomial time of the problem size n and also the inverse of the error epsilon. And there are three methods to devise FPRAS or FPTAs. These are the Markov-Monte method, the correlation decay method, and the Taylor polynomial interpolation method. The MC method, the Markov-Monte method, it gives approximation counting with random sampling, so it gives randomized algorithm. The initial FPRAS was obtained by Theorem and Sinclair, and later it was extended to ferromagnetic two-spin systems. The MC method can only handle non-negative parameters because it's based on probabilistic sampling. And the Carlo decay method was developed by Weitz. It gives FPTAs for the hardcore model up to the uniqueness threshold of the infinite regular tree. And it turns out that this technique is very powerful for anti-ferromagnetic two-spin systems. There are many FP-task results obtained for this setting, and also there are some harness results. And combine these FP-task results and harness results, an exact threshold of computational complexity transition of the partition function of anti-ferromagnetic two-spin systems is obtained, except for the critical point at the threshold. However, for ferromagnetic two-spin systems, there are only limited results. And although the above FP-task results are obtained for two-spin systems with real parameters with Carlo's decay, the Carlo's decay technique can be applied to complex parameters. Well, the Taylor polynomial interpolation method is a new method developed by Barvinok, and it was extended by Petal and Rex. It turns complex zero-free regions of the partition function into FP tasks of corresponding complex parameters. So it connects the long-standing study of complex zeros to the approximation algorithms of the partition function. And motivated by this, complex zero-free regions have been obtained for hardcore models, Yuxin models, and general two-spin systems. Now let's introduce our results. In our paper, we obtained new zero-free regions of the partition function of two-spin systems. To our best knowledge, these are the first zero-free regions in which all these three parameters are complex valued. And we also proved that for the above zero-free regions, correlation decay exists. So we obtained new correlation decay results for complex parameters. As a consequence, we obtained an FP task for bounded two-spin systems for these complex parameter settings. Well, either Weitz's algorithm or Barvinok's algorithm. Our main technical contribution is a simple but a very general approach to extend any real parameter of which the bounded two-spin system exhibits correlation decay to its complex neighborhood, where the partition function is zero-free and correlation decay still exists. Now let's formally describe our main result. We use zeta to denote the complex parameter vector, and we assume that gamma is non-zero. Then we fix the degree bound delta, and if the real parameter zeta sub 0 satisfies real contraction, real contraction is a sufficient condition for the existence of correlation decay for some real parameters, then there exists a delta that is larger than 0 such that for any complex parameter that is in the complex neighborhood of zeta sub 0, we have the partition function is non-zero for every graph. This is even true for every graph that contains some pinned vertices. And here the choice of this small delta does not depend on the size of the graph. And we also show that the delta bounded two-spin system specified by these complex parameters in the complex neighborhood exhibits correlation decay. And as a consequence, there is an FP task for computing the partition function. Well, for hardcore models and Yuxin models without external field, zero-free regions are obtained by real contraction. Now here, for general two-spin systems, we unify correlation decay and zero-freeness real contraction. We also give some sets of real parameters that satisfies the real contraction. So we define the following four real correlation decay sites. The set S1 is obtained by Zhang, Liang, and Bai. The set S2 is obtained by Li, Lu, and Yin. The set S3 and S4 are obtained in our paper, and we show that for any real parameter in one of these four sites, there exists a complex neighborhood of the parameter such that the partition function is zero-free in this complex neighborhood, and the correlation decay exists for this complex neighborhood. And when beta is less than gamma and the lambda is sufficiently large, it's known that the approximation of the two-spin systems is base hard for general graphs, while base hard is a conjectured intermediate class for the approximation of counting problems. However, here we show that there exists a p-task for such problems on graphs of bounded degree. And when beta is less than 1 and less than gamma, the p-task obtained by our set X-ray is covered by the result in Guo and Lu. And also, when beta equals gamma, Liu independently proves that a complex neighborhood of S2 is zero-free. Now we roughly introduce our approach. We first give some notations. We consider positive parameters, and we know that for positive parameters, the partition function is non-zero for any graph G and any partial configuration. A partial configuration is just a configuration on some subset of vertices. And we define the value p at vertex V to be the marginal probability of V being assigned to spin plus. And we define p at V conditioning on a partial configuration sigma to be the marginal probability of a free vertex being assigned to spin plus. And we define the ratio R at vertex V conditioning on a partial configuration sigma to be the ratio between the two probabilities that the free vertex being V is assigned to spin plus and minus. We say a vertex is free if it's not pinned by the partial configuration sigma. Well, for complex parameters, if the partition function is still non-zero for any graph G and any partial configuration, then both the value p and the ratio r are well defined. Now, in this case, the value p is just a ratio and it has no probabilistic meaning. The goal of Weitz's algorithm is to estimate the value p, and which is equivalent to estimating the ratio r. Well, when the graph is a tree, the ratio r can be computed by recursion. So suppose that V has d many children, and among its children, k of them are free. Then the ratio r can be computed using this the ratio r at these free vertices of its children. So we formally define the recursion function. A recursion function for two-spin system is defined as follows. And we know that this function is well defined and analytic when gamma is not equal to 0 and x is not equal to minus gamma. So we define its domain to be the following. And we know that the recurrence function is analytic on its domain. Well, for general graph, with reduced computing the ratio to that in a tree, and it's called the self-ordering walk tree. However, the self-ordering walk tree may be exponentially large in the size of the original graph G. So in order to get a polynomial time algorithm, we run the tree recursion at logarithmic depth and hence in polynomial time. And we plug in some arbitrary value at the truncated boundary. Now we need to bound the error introduced by this arbitrary value at the truncated boundary. We have the following notion of strong spatial mixing to bound the error. A two-spin system specified by a complex parameter exhibits strong spatial mixing if first, the partition function is not equal to 0 for any graph G and any partial configuration. This condition is to make sure that the p-value is well defined at any vertex V for any partial configuration. And the second condition is a real requirement for strong spatial mixing. It says that the difference of the p-value at vertex V under two different partial configurations is exponentially small. It's exponential on the size of the distance from the vertex V to the vertices that these two partial configurations differ. Well, we should see that the condition 2 is stronger than the usual definition of strong spatial mixing for real parameters. Well, for real parameters, we only need to consider the case that these two partial configurations are on the same subset of vertices. However, for complex parameters, we need to consider the case that these two partial configurations are on two different subsets of vertices. If a two-spin system exhibits a strong spatial mixing, then it also exhibits correlation decay. Now, we want to bound the difference between the two p-values is equivalent to bound the difference between the ratio r. So now we need to bound the rate of decay of the recursion functions. Remember that the ratio r can be computed by recursion. And we may use the potential function to map the original recursion to a new domain. And we use this f super phi to denote the composition of the original recursion function f with the potential function phi. And for a positive parameter, a sufficient condition for the bounded two-spin system specified by this parameter zeta exhibiting strong spatial mixing is that there exists a good potential function such that f super phi satisfies real contraction. Now let's formally define real contraction. We see that a real parameter satisfies the real contraction for degree bound delta if there exists a real compact interval and a real analytic function that is defined on this interval, and the derivative is non-zero for all variables on this interval, such that the original recurrence function is contracted on this interval. And also, the f phi, that is the modified recurrence function by applying this potential function phi that has some bound on its gradient. Now here, if this is satisfied, then we say that the function phi defined on this interval g is a good potential function for this real parameter. Now here, we need to make sure that the modified recurrent function f super phi is well defined. And actually, all these conditions ensures that this function, the modified recurrent function, is well defined and is analytic. And it's known that real contraction implies coordinate decay for real parameters. So it says that if a real parameter satisfies real contraction, then the delta bounded two-spin system specified by this parameter is hip with strong spatial mixing. And we can prove that for any parameter in these four sites, it satisfies real contraction. Now, if we want to generalize the coordinate decay technique to complex parameters, we need to ensure that the partition function is zero-free. So this is the first condition in the definition of strong spatial mixing. So now let's take a detour to Barvinok's algorithm. This algorithm is based on zero-free regions. Let I be a real interval, and we define a complex neighborhood of this I. It's a delta strip region. And Barvinok's method says the following: consider a graph polynomial of degree n that is zero-free in this complex neighborhood I sub delta. And then for any complex value z in this complex neighborhood, the polynomial can be approximated by using only log n minus coefficients. So this is log of n and 1 over the error epsilon. And for two-spin systems, these coefficients can be computed in polynomial time. So together we have the following result: that if the partition function of two-spin system is zero-free in a delta strip region, then there is an appetite for computing the partition function. Here we will use the partition function as a universal polynomial on the parameter lambda. Now, one way to obtain zero-freeness is by recursion. And we first assume that the partition function is not equal to 0 if one vertex is pinned to the minus spin. And then, in order to prove that the original partition function is non-zero, it's equivalent to show that the ratio r at vertex v is not equal to -1. Recall that the ratio r can be computed by recursion with self-ordering work tree. And then, the idea of the recursion method is to construct a contraction region such that it satisfies these two properties. These two properties ensure that with the initial value r equals lambda. So this is why we require that lambda is in this region Q. With this initial value, the recursion will never achieve -1. So this is why we require that -1 is not in this Q. And we require that minus gamma is not in this region Q because that we want to make sure that the recursive function is still analytic and well defined. So now we formally define the complex contraction. Still, we fix a degree bound delta, and we see that a complex parameter satisfies complex contraction for this degree bound if there exists a compact complex region will satisfy this condition. Now here, the modification from real contraction to a complex contraction is by modifying a real compact interval to a complex compact region. And then there exists a complex analytic and invert function defined on this compact complex region Q, where the inverse of this function is also analytic and P is convex. So here it's from a real analytic and invertible function to a complex analytic and invertible function. And still we require that the original recursion function is contracted. And also we have some condition on the R1 norm of the gradient of the modified recursion function by this potential function. And again, we need to make sure that this modified recursion function is well defined and analytic on its domain. These are ensured by all these conditions. And we can show that the condition one of the complex contraction is already sufficient for zero-freeness. So we have that if a complex parameter satisfies complex contraction for some degree bound delta, then the pattern function is not equal to 0 for any graph of degree at most delta. And it's even true if this graph G has some configuration. And now the reason why we require condition 2 is that condition 2 combining with zero-freeness results gives a sufficient condition for bounded two-spin system of complex parameters exhibiting Cartesian decay. So we have the following result: that a complex parameter satisfies complex contraction for some degree bound delta, then the delta bounded two-spin system specified by this parameter exhibits strong spatial mixing, and then there is an epitaphs. Finally, we give our main technical result. We show that a real contraction implies complex contraction. That is, given a real parameter satisfying real contraction, there exists a complex neighborhood of this real parameter such that all parameters in this complex neighborhood satisfy complex contraction. The idea is that we want to extend a good real potential function to a good complex potential function. First, by the unique analytic continuation and the inverse function theorem, we can show that there exists a complex analytic and invertible function phi tilde that is defined on a complex region. Then we show that this potential function phi tilde is good. The idea is that since these functions are analytic, by continuity, we can pick small enough delta and epsilon such that they satisfy some desired properties. And we let P to be the compact region. And we show the only thing we need to show is that the recursion function is contracted on this region P. And this can be proved by the following inequality. Here, the recursion value with real parameter is in the real interval I. And since the difference is less than epsilon, the recursion function value with the complex parameter is in the epsilon strip complex neighborhood of I, which is P. So the value is in P. Now let's summarize our approach. We show that these four sites satisfy real contraction. And we prove that real contraction implies complex contraction. And complex contraction gives zero-freeness and complex decay result for complex parameters. And from zero-freeness, we can get epitaphs with Barvinok's algorithm. And from Contraction decay, we can get epitaphs with Weitz's algorithm. And we should see that our approach is generic. It does not rely on a particular chosen potential function. So it works even if the potential function does not have an explicit expression. Thanks for watching this video.